We're gathered here today to talk about Newton's law of universal gravitation. But before we do that, I just wanted to share with you a scientifically proven weight loss formula. This is going to make me millions. All right, now, according to science, weight is mass times gravity. That's the formula. If you want to reduce your weight, you have two options. You can reduce your mass, or you can reduce g. There it is. Wait a minute. Wasn't g a constant? Well, it turns out g is not really a constant, so this can actually work. Or in other words, gravity is more than just mg. And that's what we're going to be talking about today. Now, Newton's law of universal gravitation was named after a man named Sir Isaac Newton. This is a portrait that he posted on Instagram the day that he filed his patent for his clever fruit-based cookies. But the story starts before Sir Isaac Newton. So let's go back and talk about the work of Tycho Brahe. Tycho Brahe was an astronomer. He was an observationalist. He observed the positions of the planets among the stars and made very, very careful records of how it changed through time. And this data turned out to be very important for what came next. Unfortunately, Tycho Brahe's work as an astronomer was cut short when he crossed a hut and ended up encased in carbonite. Well, sometime later, there was a man by the name of Johannes Kepler that came along, and he spent years learning to master the use of chopsticks. But once he'd done that, he was bored, he needed a new challenge, so he took a look at Tycho Brahe's data and was able to see some patterns in it, was able to come up with some geometric laws that described how the planets moved. Well, these laws were very empirical, and we didn't really know why they did what they did. There was no universal theorem sort of from fundamental physics. But then one day, Sir Isaac Newton was sitting under an apple tree, and an apple came and hit him on the head, and he realized that things fall down because of gravity, and since he was the first person to realize that things fell down, he invented gravity. Well, at least that's the way I heard it when I was a kid. Actually, the story goes more like this. Sir Isaac Newton looked at all of the data out there about how the planets move and the laws that Kepler came up with, and figured some interesting things out from that about the fundamental properties of gravity. And later in his life, he liked to claim that he started thinking about this problem one day when he saw an apple fall from a tree. Not onto his head necessarily. Anyway, so what Newton did was just a creative, amazing accomplishment, which I would say is even greater than the cookies he invented. And that is he was able to figure out a way to tie his laws of motion, in particular his second law, F equals ma, and is able to describe how the planets move in terms of forces. And what he was able to do was he was able to show that Brahe's observation and Kepler's laws can be derived by assuming that there is a force between the planets which is equal to a constant times the mass of one planet times the mass of the sun or the other planet or whatever, divided by the distance between them squared. So the fundamental thing, I guess there's several great leaps in Newton's law of universal gravitation. The first one is this idea that there's a force that drops off as 1 over r squared. Being able to realize, see, back before Newton's law of universal gravitation, people really didn't know why planets took the paths that they did. I mean, Kepler was able to tease out of Brahe's data sort of the fact that the planets had these elliptical orbits and how the periods of the orbits were related to the radius of the orbits and things like that. But, why did they do it? They're just following some natural path. People knew that things fell when you dropped them, but there wasn't really a physical explanation as to why. And Newton was able to come around and say, well, look, if there's a force that acts between two bodies that drops off as 1 over r squared, then you can get these orbits that Kepler found. And if you make that force proportional to the mass of the object, then everything falls at the same rate like it should. But where does this force come from? And Newton, a third brilliant idea was that mass itself creates this force, that any two things with mass will exert forces on each other according to this equation. Now, the direction of the force, this equation gives the magnitude. The direction of a course is, of course, towards the object that's exerting mass on the other object, right? So the Earth pulls you towards it. You pull the Earth towards you. With that, then, we can explain how the planets move. And people were able to do things like discover planets that hadn't been discovered yet based on their gravitational effects on things and so forth. Now, because Newton had proposed this law that said, hey, the planets, the reason they move is there's this force due to mass, that implies that this force must be acting between smaller objects, like between me and my cat and things like that. There should be a way to measure that. Well, it turns out that gravity is really, really tiny. All right, it's just a small force. It's also really, really big, right? It's the force that governs the evolution of the universe. Gravity's big on planet scales and larger because there's just lots and lots of mass, and forces due to things like electromagnetism cancel out because it just so happens that there's about as many protons as neutrons in the Earth, right? But on smaller scales, gravity is really weak, right? Electromagnetic forces, the charged particles in your hand allow you to pick up a baseball and throw it, right? And those are really big forces compared to the force of gravity pulling the ball towards your hand. So when you deal with small masses, gravity is really hard to actually measure at all. But Cavendish came up with this great experiment where he had a wire and he suspended some masses, and then he had some other masses, and the gravity from the masses would make the wire twist. And if you're really careful to make sure that you do everything just right, you can actually make gravity make the masses twist, and you can measure that constant, G, the gravitational constant. And over the years, that has been measured more and more precisely, but it's still not known super precisely. Gravity, they say, is the least understood of all of the forces. And one aspect of that is it's really hard to measure that gravitational constant. It's a particular physical constant that is just not known to that many digits, honestly, compared to other constants. But we can get it, and now knowing what that gravitational constant is, we can look out into the universe and use this law of gravity to figure out how much mass there is in different places, figure out how planets move around stars, how stars move around each other, how stars move around the black holes at the center of the galaxy. Einstein came along and advanced our understanding of gravity, and now we've got black holes, and we have light being bent by gravity. And then people looking at how galaxies moved, using Newton's law of universal gravitation, they were able to figure out that there was mass that we couldn't see in these galaxies holding everything together. And we ended up coming up with the theories of dark matter and dark energy and all kinds of crazy stuff, all based in Newton's cool law. All right, so now in this lecture, we're going to stick to the very basics of Newton's law of universal gravity. And here's the type of problem we can work with that. From astronomical measurements, we know that the Earth orbits the Sun with a mean radius of 1.496 times 10 to the 11th meters. Knowing that the Earth circles the Sun once a year, what is the mass of the Sun? Can we use the gravitational force that Newton figured out in order to find the mass of the Sun? Well, yes, we can. This is how we know the mass of the Sun. All right? Because the force due to gravity on the Earth is just G times the mass of the Earth times the mass of the Sun divided by the distance between the Earth and the Sun squared. Well, force is mass times acceleration. So the force on the Earth to the Sun is just going to equal the mass of the Earth times its acceleration. And so we can solve this equation and find that the acceleration of the Earth is proportional to the mass of the Sun. Well, we also know that for something going in circular motion, the acceleration is v squared over r. Now, the Earth doesn't do a perfect circle around the sun. It does an elliptical orbit, but it's close enough. So let's pretend like it's a circular orbit. And with this, then we can say, look, I can solve this equation over here for the mass of the sun in terms of the Earth's velocity, the radius of the orbit, and g. Well, the velocity of the Earth's orbit is just 2 pi times the radius, the circumference of the orbit, divided by the period, the distance we travel in 1 year divided by a year. And so you plug that in for the velocity, and here's an equation now for the mass of the sun. And if you plug in all of the numbers, you find that the sun has a mass of about 1.99 times 10 to the 30th kilograms. All right, you can also have non-circular orbits. As I mentioned, the Earth's orbit is more like an ellipse. Well, it's elliptical, not circular. So in general, bound orbits, where you stay stuck to the sun, are ellipses with the sun at one focus. And of course, a circle is just a special ellipse where the semi-major and the semi-minor axes happen to be the same. As you get more energy, though, you can have an object that is not bound to the sun, and you can have a parabolic or hyperbolic orbit where it's not really so much of an orbit as you pass by, get deflected, and then fly off and never come back. All right, but we're not going to actually do math with non-circular orbits in this class. Now, what if you have something that's not a point? Right, when we calculated the mass of the sun, we kind of just assumed, we treated the Earth and the sun like point masses. And, they're far enough away from each other that maybe that's not a bad approximation. But what if you wanted to, for example, find, the gravity that a cube pulls on a point with? So imagine, you're hanging out with the Borg and you want to know how much gravity is pulling on your ship, pulling it towards the Borg cube. Well, if we have an equation that works for point masses, we can always break our cube up into an infinite number of infinitesimal pieces and do an integral of all of the little infinitesimal masses that make it up, and then find the net force by summing up the force from each one of those cubes. And that can be a real pain in general. Spheres, it turns out, are special. If I take a sphere and dice it up however I want to and add up all of the little pieces, it turns out that the gravitational force due to a sphere of mass is just the same as if there were a point with all of the mass at the center of the sphere. So pretty cool. So with that, we can do problems like this. What is the acceleration of gravity at a distance from the surface of the Earth equal to the radius of the Earth? Right now, one Earth radius away from the surface of the Earth, it's really not a good approximation to treat the Earth as a point. But it turns out that for a sphere, the gravitational force is the same as if that sphere were, all the mass from the sphere was concentrated at a point. So now we can work that problem. So we're going to say, look, the force of the Earth on this object is equal to the mass times the acceleration of the object. But because the Earth can be treated like a point, that force is just g times the mass of the Earth times the mass of the object times 1 over the distance from the center of the Earth to the object squared. We can once again solve this for the acceleration due to gravity, and we get it's just g times the mass of the Earth divided by the distance from the Earth to the object squared. Okay, well, the distance from the Earth to the object in this problem is just twice the Earth's radius, right? The object is 1 Earth radius above the surface. That means it's 2 Earth radii from the center of the Earth. But of course, if we were just right on the Earth, the acceleration due to gravity would just be g. So if I plug in just the radius of the Earth for the distance between the center of the Earth and the object, I would get g. So I can write my acceleration up above the Earth in terms of the acceleration at the surface of the Earth, right? I just square this out and I get 4 radius of Earth squared, and that's just then g over 4. So the acceleration due to Earth's gravity, 1 Earth's radii above the surface of the Earth, is 1/4 the acceleration of gravity at the surface of the Earth. And it turns out that it's not just spheres that are special. Spherical shells are special. So, for example, if I had an arrangement of mass, which was a hollow sphere, so just a shell, a spherical shell. Now I've cut my spherical shell in half so that we can see inside of it, but this really only works for the complete spherical shell. If you're sitting outside a spherical shell of mass, you can treat that shell as if it was a concentrated point of mass in the middle. In other words, the force due to gravity from that spherical shell is the same as what you would get if you had all of that mass concentrated in the center of the spherical shell. And that's really nice because oftentimes you have things like planets and stars that are not uniform solid spheres, but we can treat them as kind of having a radial symmetry, that the center is maybe a different density than the outside, but there is some symmetry such that I can kind of just add up the different pieces of the sun as little spherical shells, slices, and each one of those spherical shells pretends like its mass is right at the center of the sun. And so that makes life a lot simpler when we're doing celestial mechanics. Well, this is what happens if you are outside of the spherical shell. For an object inside the spherical shell, it turns out that the gravity from all the different little pieces of the shell all cancel each other out. And inside the spherical shell, you get no mass, you get no force due to gravity. So now we can use this knowledge to solve this problem. A person weighs 180 pounds on the surface of the Earth. If they could dig a hole halfway to the center of the Earth, what would their weight be at the bottom of the hole? Treat the Earth as a sphere with a uniform density. Well, the force due to gravity is just G, right? Because the Earth is all of these different spherical shells, but the ones, if we dig a hole and go down to the bottom of the hole, the shells above us, their gravity cancels out, and so we only have to worry about the shells below us. So the force due to gravity is just G times the mass of the person times the mass of the Earth underneath them, the part of the Earth that is at a distance from the center of the Earth smaller than the distance of the person, all divided by the distance of the person from the center of the Earth. All right, well, the mass underneath the person is just density times the volume underneath the person. And if we're treating the Earth like a uniform sphere with constant density, then that density is just the mass of the Earth divided by the total volume of the Earth. Well, the volume of a sphere is just 4/3 pi r cubed. So we plug those in here. The mass underneath them is 4/3 pi r cubed. The mass of the entire Earth is 4/3 pi radius of the Earth cubed. The 4/3 and the pi's cancel out, and we get this. And then we can further simplify that. And here's our equation. There's the force due to gravity if you are standing a distance r from the center of the Earth underneath the surface of the Earth. And, well, of course, G, mass of person, mass of Earth, divided by the radius of the Earth squared is just the acceleration at the surface of the Earth. So we can write the force due to gravity as just your radius divided by the radius of the Earth times G. This is as long as r is less than or equal to the radius of the Earth. So if you dig a hole down halfway to the center of the Earth, your distance from the center of the Earth is just the radius of the Earth divided by 2. You plug that into the equation, and you find that the weight of the person at the bottom of this hole is just, well, the force due to gravity is G/2, which means their weight is half what their weight would be on the surface of the Earth. So, a simple weight loss solution is live your life in the bottom of a very, very deep hole. You're welcome. All right, now, gravity is a conservative force. Therefore, we can think of gravity in terms of potential energy. When we're near the surface of the Earth and the acceleration due to gravity is a constant, and we pretend like the force due to gravity is just m times g, the gravitational potential energy is mgh. But if we're moving further away and we can't just treat acceleration due to gravity as a constant, we can still find a potential energy from the force due to gravity, due to Newton's law of universal gravitation. So remember, you find potential energy by finding the work, the negative, the work done by the force, and the work done is just the integral of force times distance. So if we take an object and move it away from the Earth, the force of the Earth is this, and of course the displacement, as we move it away from the Earth and give it more potential energy, the displacement is in the opposite direction from the force, and so we lose that minus sign right there. It cancels out. Well, m1, m2, and g are constants, so they come out of the integral. And the integral of 1 over r squared is just negative 1 over r plus a constant. All right, so that is the gravitational potential energy that we get from Newton's law of universal gravitation. Now, the constant, of course, can be anything at once. The physics will all work the same no matter what constant you tack on to any potential energy, as long as you are consistent in what constant you use. Well, the general thing that people tend to do is just set that constant to 0, so we don't have an extra thing to drag around. All right? And so it turns out then that gravitational potential energy, if we set that constant to 0, is just negative g m1, m2 over r. And so basically what this is saying is, if you are infinitely far from the Earth, you have no gravitational potential energy. And as you fall towards the Earth, and r gets smaller and smaller, your gravitational potential energy gets larger in magnitude, but it's going negative. So you are indeed losing gravitational potential energy as you fall towards the Earth. So here's a problem we can do using gravitational potential energy. A piece of space junk, which is a distance of 1 Earth radii from the surface of the Earth, is initially at rest with respect to the Earth. Then it falls. How fast will it be going when it hits the atmosphere? Well, we're going to assume that the top of the atmosphere is very close to the surface of the Earth. So basically, we're going to find how fast it's going after it's fallen to the surface of the Earth. Well, this is just a conservation of energy problem. Energy initial equals energy final. Our initial energy is just gravitational potential energy. Negative g, mass of the junk, mass of the Earth, divided by 2 Earth radii. Right? The junk is 1 Earth radii away from the center, or from the surface of the Earth, which means it's 2 Earth radii away from the center of the Earth. The final potential energy is negative g m junk mass Earth divided by the radius of the Earth, right? The final position is it's 1 radius away from the center of the Earth because it's at the surface of the Earth. But now it's lost potential energy, but it's gained kinetic energy, 1/2 mass junk times velocity squared. And now we can solve this equation for velocity. And when we do that, we just get g, mass of the Earth, over the radius of the Earth. All right? Well, now we have to look up the mass of the Earth and the radius of the Earth in order to solve this problem. But we can make it a little simpler by multiplying the fraction inside the square root by radius of the Earth over the radius of the Earth. And then notice this right here, g mass of the Earth over radius of the Earth squared. That's just the acceleration due to gravity near the surface of the Earth, or g. So now I only have to look up the radius of the Earth, and I do that, and I plug it in, take my square root, and I find then that the velocity is 7.9 times 10 to the 3 meters per second, or 7.9 kilometers per second. Pretty fast. It's going to make a bright glow. We can also use this understanding of potential energy to calculate the escape velocity. What is the escape velocity? Well, if you ignore, drag due to air or whatnot, the escape velocity is the velocity you need to have in order to get away from the Earth forever and never come back. Right? Imagine we're just above the atmosphere, so we don't have to worry about drag due to the air, right? Imagine we're on a space station and we shoot a projectile away from the Earth. Right? It's going to go up, but it's going to slow down as it moves, right? Because the Earth's gravity is pulling on it. And if we don't shoot it up fast enough, eventually it'll turn around and fall back down, back to the Earth. But if we shoot it fast enough, it'll eventually get away and never come back to the Earth, right? Or if we shoot a satellite fast enough out of the solar system, eventually it'll get away and never come back to the sun. The velocity you need in order to get away is known as the escape velocity. What is the escape velocity equal to? Well, once again, this is a conservation of energy problem. So E initial equals E final, but we want E final to be 0. We want our object to have just enough velocity, just enough kinetic energy that when it gets out to, that it can get all the way to infinity. When it gets to infinity, it's okay if it doesn't have any velocity. It just needs to get to infinity so it never comes back. All right? So the minimum energy that we need is enough kinetic energy to get to infinity with no kinetic energy left. If we have any more, we can get to infinity with kinetic energy left, but the escape velocity is the minimum velocity we need. Okay, so E initial equals E final, which has to equal 0. So E final is 0, right? Because the potential energy at infinity is 0, and we want our kinetic energy there to be equal to 0. So we just have to find E initial and set that to 0. Well, E initial is 1/2 mv squared. All right, and that E is for escape, not Earth. I just realized that's confusing. So 1/2 m escape velocity squared is our kinetic energy. The potential energy is negative g, mass of the object, mass of the Earth, divided by the radius of the Earth, right? Assuming that we're shooting our object from the surface of the Earth. If we're shooting it from some higher distance, we would calculate our escape velocity by putting the correct distance in there. All right, and then we just solve this for the escape velocity, and this is what we get. Now, this is a general principle. It doesn't just apply to the Earth. It applies to any gravitational sphere. All right, so in general, the escape velocity to get away from a planet or a star is just 2g times the mass of the thing we're getting away from, divided by how far from the center of that object we're starting out. All right, that is the end of our discussion of Newton's law of universal gravitation. Here's a quote by the famous physicist Paul Dirac. Pick a flower on Earth and you move the furthest star. Remember, everything in the universe is connected ever so slightly by gravity. You've been a good audience. You paid attention. I'm sure your brain is getting tired. So treat yourself to a Fig Newton and take a break.